Okay, so let's look at this example. So we consider the basis of the null space. So again, the basis has to satisfy the two requirements, which has to span the given subspace, and also those vectors in the basis should be linearly independent, which means we have to remove the redundancies. So in this case, suppose this matrix was reduced into this reduced echelon form, and then we would do this kind of process of moving all the free variable on to the right, and then factor them out in order to obtain this parametric vector form. So so we can choose any values for x2, 4, 5, and so this subspace can be represented as a span of these three vectors. Let's call v1, v2, and v3. v1 and v2 and v3. So we satisfy the first condition of spanning our given subspace, because the null space is represented as the span of these three vectors. And then the next question is, are these three vectors over v1, v2, v3 are linearly independent? So the answer is those vectors, or these vectors that you will obtain after you factor them out to obtain this parametric vector form, these vectors are always linearly independent. And yeah, let me give the reason. So given these three vectors, how do we check if they are linearly independent or not? We consider it's a homogeneous linear system, right? And this is already a vector equation, and so let's check. Let's make this entire part as 0. Okay, so this is a homogeneous linear system, and then we can check whether these values can have a non-trivial solution or not, right? But the x2, 4, 5 should be always 0 in order to satisfy this equation, because so let's look at this row and this row and this row, or this row and this row and this row. So all the three rows are corresponding to the free variable of x2, 4, 5, right? And then if you imagine how we've formed this these vectors, okay? So for each free variable, so for example x4, and then in this place we will always have a 1, right? Because that was just a free variable, right? And so this guy will be the same as this x4, right? So simply, in order to obtain this second vector, we just set this value as 1. Okay, then what about the other values corresponding to the other free variable? So here the question is, in the place of free variables x2, 4, 5, we only have just x2, 4, 5 each, right? So in this second, fourth, and fifth row, it doesn't involve any other free variable, right? So in this place, it will only have x2, right? No other variables like x4 and 5, which means in this place, we obtained 1, but the corresponding rows in this other free variables, these values will always be 1. Okay? And then, if we imagine the vector equation of a homogeneous linear system, we will have to basically set all the rows to be 0, right? And so, in order to make the second row to be 0, which means if we extract out the second row, it will be like x2 times 1, okay, x2 times 1 plus 0 times x4 and 0 times x5. And so 1 times x2 equals 0. And so we obtain x2 should be 0, right? And then likewise, if we use the fourth equation, the fourth equation will become x2 times 0 and x4 times 1, x5 times 1. And so x4 should always be 0 in any cases. x5 is also the same case. So in order to set, or in order to make this linear combination as a homogeneous linear system, we have to set x2, 4, 5 always 0. Okay, and so we can, our conclusion here is that we will only have a trivial solution, right, in this type of a parametric vector form from homogeneous linear system. And so we can conclude that these vectors are linearly independent. Okay, so in this case, let me ask the question. So what is the dimension of this null space? What is the dimension in this particular case? The dimension should be 3, because these three vectors are linearly independent and span our null space. And also, what is this number of 3? So that comes from the number of our free variable, right? And so when considering the null space, the dimension of the null space is the number of free variable, and also we consider the column space, right? And so column space, the dimension of the column space was the same as the number of pivot variable or non-free variable. Okay, so when adding those two dimensions, the dimension of column space and dimension of null space, and then we will always have the total number of variables. So in this case, the dimension of the null space is 3. And then what about the dimension of column space? So we have 2 pivots here, and then we bring these 2, okay, in order to obtain the column space. And so the dimension of the column space was 2. So these 2 and 3, adding them up, we will always that will always be equal to 5, right? So that was one of the theorem that we learned last time. And then let's see. And the dimension of the column space, we learned the new term, specifically referring to this term. What was that? What was that? The name of the term, or the name of the dimension of the column space was called rank, right? So rank of matrix A is the same as the dimension of column space, and that is also the same as the number of pivot variable. Okay. Okay. So that was called this rank theorem. Then I was explaining this basis theorem. Okay. So let's look at this example again. Okay, let's first look at the column space. So the column space, the dimension of the column space is 2, right? And then, this is the entire universe is R3, right? But those two vectors are like those two fingers that forms this subspace of this plane, right? And also, okay, so what is the basis? One particular example of basis, this guy and this guy, right? So those two are basis. Then let's see. So these are the two bases, right? And then you guys remember this figure, and then also I drew another figure that is mapping each point there into just a two-dimensional space, right? And so that was, that relationship, or this mapping relation from this slanted surface or plane into just a two-dimensional space. That was one-to-one mapping, and that mapping was called a isomorphism. Okay, that was called a isomorphism. Okay, and then this vector if you remember the b coordinate, which we learned in the beginning of the last lecture, this is corresponding to those two very basic vectors. Okay, so these two will become our new basis, right? So so in this case, even though they are living in the three-dimensional space, but if we think about this two-dimensional space, x1 and x2, for example, this guy, v1, will become this vector, right? v1, and then the new coordinate of this v1 will be 1, 0. And then, let's call this guy as a v2, and then v2 will be mapped to another vector in this two-dimensional space as 0, 1, right? Okay, so in this case, let's consider this situation. Suppose you pick up one vector in this subspace, and then this point will be somewhere around here, okay? And then suppose this vector was 3, 5, 2, for example, okay, in this three-dimensional space. But this this vector will be mapped to maybe 1, and 2.3, right? So that's how we obtain this parallelogram here, right? Okay, so this guy will be mapped to 1, 2.3. So that way we can consider this kind of one-to-one mapping. Okay, and then here, let's look at this situation. So what is the rank of this subspace? It is spanned by two linearly independent vectors. So the dimension is 2, right? And then, the situation is we already know the rank, the dimension of this subspace. Okay, so the dimension of the subspace is known, and then we select these some number of vector, but those number of vector is just set as 2. Okay, so let's consider picking up the two vectors from this space. Okay, any two vectors. So one student may pick up this vector and this vector, and then another student may be picking up this vector and this vector. Okay, so let's consider this any set of vectors, but the number of vectors are just 2, which is the same as the dimension of these subspace. Okay, and then if these two vectors are linearly independent, and then it will automatically span this subspace. So we are trying to currently what we are doing is to try to relate this guy into the basis of this subspace. So again, the basis, the two condition of the basis is linearly independent, and also spanning the subspace, the given subspace. Okay, and then the dimension of the vector is the dimension of the subspace is 2, and then if we selected the two the vectors that are not yet bases, okay, but if these vectors are satisfying one of these two conditions, and then the other condition is automatically satisfied. So that is the last theorem in this chapter. So in this case, for example, if we selected these two vectors, and then we don't know yet that if they are linearly independent, but we know, we assume that, or we check that these two vectors are spanning our subspace, and then these two vectors should be linearly independent. And then, on the other hand, if these two vectors are linearly independent, then they will automatically span our subspace. Okay, so this is the theorem that we are currently studying, and let me explain why. So the book skipped the details or the proof of it, but I'm going to give you kind of a conceptual proof. So picking up one vector from this subspace is the same as picking up the vector in this two-dimensional subspace, right? So picking up this vector is the same as picking up this vector. And then if the two vectors here are linearly independent, then the original vector in this three-dimensional space will also be linearly independent. Okay, so the two vectors are linearly independent. They should be along the same line, right? So in this mapping from like this parallelogram, so this is a 1, 0, and this is a 0, 1, and then we are just doing this parallelogram into this regular grid. So this is a 1, 0, which is mapped from here, right? And so if the two vectors are not along the same line, and then the corresponding two vectors in this two-dimensional space is not along the line, right? So if the two original vectors were linearly independent, and then the linear independence is also the same in this subspace. And also, if these two vectors are spanning our subspace, and then these two vectors will span these two-dimensional subspace. Okay. Okay, then let's understand this theorem. So the dimension of this subspace is 2, and then we are picking up the two vectors. But instead of picking up here, we pick up the vector from this two-dimensional subspace, and then suppose they are linearly independent. And then suppose the two vectors were something like this guy, 1, 2, and 3, 1. And then collecting them as columns of a particular matrix, we will always form the square matrix. Okay, so we will always form the square matrix here. Okay, so in that, why do we obtain the square matrix? It is because if the subspace dimension was 2, and then it will be always mapped into this two-dimensional subspace. And also, if our subspace was originally three-dimensional space, and then it will be mapped to just a regular grid type of a three-dimensional subspace, three-dimensional space. Okay, so in this second space, we will always end up picking up the same number of vectors. Okay, because the same number of vectors as the number of the elements of a particular vector. Okay, so if we consider this a square matrix, and then we can utilize invariable matrix theorem. So if these two are linearly independent, and it means it only has a trivial solution. It doesn't have any non-trivial solution. And also, if our matrix is square, and then linear independence or no free variable is actually the same as we are spanning the entire two-dimensional space, right? So linear independence means we have to have a pivot in every column, but because we have the same number of rows, we will also have a pivot in every row, right? So if the two vectors are linearly independent, and then they will automatically span the entire two-dimensional space. So we are spanning this entire two-dimensional space, and then it is the same as we are spanning this slanted slanted plane in the original three-dimensional space. Okay, and then the next one is, so what we showed here is if they are linearly independent. I mean, we picked up the two vectors and that are linearly independent, and then they will automatically span our entire our two-dimensional space. And then let's think about picking up the two vectors that are spanning this two-dimensional space. And in this case, it is the same. So we picked up another set of vectors, and then someone told you those two vectors are spanning the entire two-dimensional space. In this case, it means we have to have a pivot in every row, right? And also, in this case, every column should also have a pivot. Okay, so that way, if they are spanning the entire two-dimensional space, and then they should be automatically linearly independent. Any questions? Okay, and let me give just one additional explanation in order to easily understand this fact. So, suppose you are given a particular subspace, and that is for example, this kind of two-dimensional subspace, and then the dimension is 2, right? And then at least the number of vectors, the number of vectors that you need in order to fully span your subspace, that should be actually 2. So if the dimension of the subspace is 2, and then you cannot fully span your subspace using less number of vectors, right? So if your subspace is a 3-dimensional or 5-dimensional, and then it is impossible. I mean, it is never possible to span your subspace using maybe 4 vectors or 3 vectors or 2 vectors. Okay, so it is never possible. Okay, and then also if you picked up more vectors than the number of dimensions. So for example, in the 5-dimensional space, and then you picked up maybe 6 vectors, and then they should be, it is never possible that they are linearly independent. So they should be linearly dependent. Okay? Okay, so that is about this theorem 5. Okay, then this is the last slide of the chapter 2, and it is quite easy. So what we are doing here is, so we studied the list of items in the invariable matrix theorem, and then we are adding a few more items into the invariable matrix theorem. Okay, so here the situation is still the matrix A is invariable, and the question is when your matrix is invariable. So if one of these conditions are satisfied, and then your matrix is invariable, and then let's look at that condition. Okay, so in the case of 3 by 3 matrix, if this matrix should be invariable, if this matrix is invariable, and then what should be its reduced echelon form. So 3 by 3 matrix, and then if we consider or change this matrix into reduced echelon form, what should be the reduced echelon form? Identity, right? Okay, great. So it should always be reduced into this identity matrix, right? And which means you guys know that the columns should be linearly independent, which means no free variable, right? Okay, then let's use the new terms or the new concepts that we learned in this chapter. Okay, so in this case, column space of an A should be spanning the entire three-dimensional space, which means we are having the pivots in every row, right? And so the linear combination of these three vectors should completely fill up the three-dimensional space, right? By the fact that the pivots are existing in every row. Every row has to have a pivot. Okay, and then O, the dimension of the column space of an A should be n, because we are talking about the three-dimensional space or the entire three-dimensional space. What is the dimension of these entire three-dimensional space? Or what is the linearly independent vectors that are spanning your three-dimensional space? That should be 3, right? So the dimension should be 3 because it's a 3 by 3 matrix. Again, we are only considering n by n square matrix. Okay, and then dimension of the column space is having another name of rank. So O and P are the same. And then Q, P, R. You guys know that the dimension of the column space is n or 3, and then there is no free variable, and so the dimension of the null space should be what? The dimension of the null space should be the same as the number of free variable. So we have no free variable. So the dimension of the null space is 0. Then the null space of A that has a 0 dimension will always contain only the 0 vectors, which is a trivial solution. There is no non-trivial solution. Okay, and then also okay, we skipped this M. Then let's look at this M. The columns of A form the basis of Rn, right? So the column will entirely span the three-dimensional space. So all these, any of these are satisfied, and then also your matrix will be invariable.
Q is the same as R. Q.
Q. Q is the same as R. Yes. Yeah. So the dimension of the null space is 0, which means you have no free variable, right? Because the number of free variable is the same as the dimension of the null space. And then no free variable means you will have only the trivial solution for homogeneous linear system. And then what is the null space? That is just the same as the set of all the possible vector x that is satisfying this homogeneous linear system. And so that vector will only contain a 0 vector. Okay? Any questions? Okay, that's the end of chapter 2. Okay, and then So the next chapter is about. So the next chapter is chapter 3, and chapter 3 is about the determinant. But for this determinant, so I'll just ask you guys to study yourself. So I'll give you 2 online lectures, which are the most famous, linear algebra online lecture. And that lecture is much better and much insightful than how this book is describing this determinant. So although you already received the homework due next Monday, but you guys have another homework to watch those determinants. But it will have the deadline in later days, like maybe later next week. Okay, and one lecture is about maybe 1.5 hours or so. Maybe it's less than that. And so yeah, please spend maybe 3 hours to just watching that lecture. Yeah, watch that lecture. Okay, and then after that, I will give you the exercise, homework as the next, from the exercise just usually from chapter 3 in this book. Okay, so I'll send the announcement about it soon, and then we will completely skip chapter 4. But we will study chapter 5. But before then, I decide to move. I decide to study chapter 6 first. 6, okay? Okay, so the 6 is about this orthogonality and least squares. And orthogonality, okay, by looking at this term, so this is a mathematical term, and this is another term that has the same meaning as perpendicular. Okay, perpendicular, like this, having two vectors having a 90-degree angle. Okay. Okay, and then let's consider maybe 3 vectors. 3 vectors that are orthogonal to each other. So, that means you pick up any of the 2 vectors among these 3 vectors. Each pair should have 90-degree angle. So these 2 vectors should have a 90-degree, and these 2, and these 2. Okay. And let me ask one question, even before studying anything in this chapter. The orthogonal vectors, or the set of orthogonal vectors, which means each of them are having a 90-degree angle, in these cases, are these linearly independent? Or in other words, is it possible that they are orthogonal to each other, but they are linearly dependent? Is it possible? So if the 2 vectors are considered, if we consider the 2 vectors, and then orthogonality is about the angle, right? Angle being 90-degree means orthogonal, right? And so in the case of 2 vectors, and then these 2 like coinciding vectors, which is along the same line, this one is a linearly dependent case. What is the angle between them? Angle is 0, right? And then if the angle is maybe 1 degree, and then they start to become linearly independent. But still, they are quite similar, right? In the sense that they so these 2 vectors are almost linearly dependent, although they are linearly independent. But let's look at so let's assume that we have a sun here, okay, and then they are shedding the light, okay, and then this direction of the shedding the light is orthogonal to this vector, okay, So when shedding the light perpendicular to the first vector, and then the second vector is almost visible. I mean, the second vector will be mostly revealed, which means this vector is projected onto this vector, which means the shadow of the second vector will be this vector, right? So if we consider like this kind of parallelogram of this vector, and then this vector is the summation of this vector and this vector, and then the visible part by the previous vector is almost containing the almost the entire part of the second vector. And after removing them, okay, after discarding or subtracting this visible part by the previous vector, and then it will only have very small amount of a vector, very small fraction, right? So in that sense, this vector is like almost linearly dependent. And then what if they are having the orthogonal vector? So the second vector is this guy, okay? And this guy, whether they are tall or small, this vector is not visible at all by the first vector, right? So in that sense, the second vector doesn't have any part that can be explained by the previous vector. Okay. So in that sense, we can think about the being maximally linearly independent when they are having a 90-degree angle. Okay. So we will do this kind of process, and then what we can do is so in this case, let's think about one more case. Initially, we are given these two vectors, okay, and then consider their span, like this, having a very small angle, but still the span is this kind of two-dimensional subspace, two-dimensional plane, right? And then after removing the redundancies from the second vector, then we can actually orthogonalize these two vectors, right? And in that case, the second vector is not containing any vector or any redundancies that can be explained by the previous vector. Okay, so in this case, we can if we consider the span of these this plane, the span of these two vectors will still remain the same, whether using this set of vectors or this set of vectors. Okay, so the situation is typically as follows. So you are given a set of vectors that are linearly independent, and these vectors are forming a particular subspace. And then you want to remove from your bases, okay, among each other. So in this case, you can orthogonalize these vectors so that they can be maximally linearly independent. So like, if we use a three fingers or three-dimensional subspace, so suppose these are your bases, okay? So these three basis vectors will still span the entire three-dimensional space, but what about this guy? This guy doesn't have any redundancies between any two vectors. So this vector, this set of vectors are much more and cleaner basis vectors. Okay, so that will, by cleaner I mean that. Okay. So in order to define the orthogonality, we first utilize, or the core concept is this inner product, and you guys know the inner product, right? So 1, 2, 3, then maybe 1, 0, minus 1. So this is an inner product between V1, V2, V1 and V2. right? And then the operator or mathematical notation for this inner product is this like a thicker dot. Okay, and that is the same as actually this guy, U transpose V. So the inner product between the two vectors are this guy. So in this case, we shouldn't use this thicker dot, because this should be just a matrix vector multiplication, but this guy can be represented as this guy, 1, 0, minus 1. Okay, so the inner product between the two vectors are the same as just a vector multiplication, but the first vector should be transposed, right? The first vector should be the row vector. Okay, and this is called the inner product and the dot product. And then they will satisfy this commutative law and this associative law and this scalar multiplication. Distributive law in this scalar multiplication, and this guy, the last thing. So we now consider the same vector, the inner product between the same vector. So for example, in the case of two-dimensional vector, x1 and x2, so this is your vector. And then, so let's call this vector as an x. And then, what if we do the dot product or inner product between the same vector? And in this case, so we have to transpose x transpose x, right? So x1, x2, and x1, x2, right? And then x1 squared, x2 squared. Okay, so it's basically sum of the squared elements. So we first square the elements and then sum them up. So that is the same as the inner product of the same vector. And this guy should be equal to or greater than or equal to 0, right? And this guy is having the same. This guy has actually the meaning of the length of the vector, right? So if we consider maybe 2, 3, 4 in the two-dimensional space, and then 3, 4, 3, 4. So this will have 5 squared, right? And then this will be this Pythagorean theorem, and this will correspond to the square, the value of the length of this vector, right? So the length, okay, the vector length, how long the vector is actually defined mathematically by using this inner product. Okay, and then this length, more mathematical term that has the meaning of this length is called a norm. Okay, this norm. Okay, and in order to represent the length of a particular vector, we use this double bar. Okay, so 3 and 4. Okay, so this is 5, and this is representing the length of the vector, and this guy is actually the inner product between the same vector, using the same vector, and then the square root of it. Okay, so it's like 3 squared and 4 squared. Okay, so this is the definition of the length of a vector, which is also called a norm. Okay, and then what about just a scalar multiple of a particular vector? So if we have a vector here, maybe 3, 4, and then maybe 2 times 3, 4. And then we have to compute the length of this vector. And then it is like 2 times and 2 times the original vector length. Okay. And then what about the negating the vectors? So we actually reverse the direction of the vectors. Then, huh? Yeah, so this guy is 5, right? So this guy is 10. The result is 10.
Why 5, 4?
Y 5, 4. So this is 5, and you said 4? You mean here? Oh. 네? 이거요? 이거? 이거요? Ah, so this is 3. Yeah, sorry for bad handwriting. And, okay, it's quite simple. So far, so good. Okay, and then using this scalar multiple, we can actually make or reduce or extend the length of vector to be always 1. So in this case, 3, 4. So we want to preserve the direction of this vector, but still we want to make the length of the vector to be 1. In this case, it is like 1/5 and 3, 4, right? So this, in this case, 3, 4 became the vector of the length 1, right? So this is called a unit vector. So unit vector is simply the vector that preserves the same direction, but the length was changed into 1. Okay. And then in this case, we can just simply divide the norm. Yeah, divide this vector by the norm of this vector, which is 5. Okay. And then here, I have a typo here. So up to this point, it is good because it's 1/5. And it should be multiplied with the vector v, not the vector length, right? Okay, so here the important part is we preserve the direction. Okay, so this is also a kind of preview of what we will learn. So if we have this 2 vector, and then what we do is to actually orthogonalize these 2 vectors. So they are just linearly dependent. They are just linearly independent, but they are not maximally linearly independent, right? So we want to make them maximally linearly independent, but at the same time, each vector, we want to make the length of each vector to be 1. Okay, so the first, using the first vector, so we make the vector of this length of this vector to be 1, and then we shed the light, okay, here, and then this guy will be decomposed into some shadow and then some invisible part, okay. And then we remove this shadow, and then the invisible part is something like this. But the length of this finger will be smaller than the original vector because this kind of parallelogram thing. The original vector length was forming the diagonal length of this rectangle, and so this is an invisible part, right? Which is now maximally independent, and then we just shrink the vector length as 1. And then what about we have a third vector? And third vector, we just shed the light and then remove the part that is explained by the first vector, and then also we shed the light from this vector onto the second vector that is maximally independent with the previous vector, and then this vector is having okay. Now, so we define the length of the vector, or also known as norm, and then we now consider the 2 vector. u and v, and then consider the distance between them. So what is the distance between these two vectors? So the first one and the second one. Okay.
Excuse me, there's a missing square, the missing 2 on the...
Right. Yeah. Sorry about that. Yeah, that's a good point. Okay, so when defining the length, the distance of the two vector, then we first consider one vector, or we change it to one vector as a difference between these two, and then we use the newly defined notion of the norm of the vector. Okay, so that is the meaning of the distance. Okay, now it's time to mathematically define the orthogonality, or having the 90-degree angle. So maybe you guys already learned that if the two vectors are, the inner product between these two vectors are 0, and then it is the same as their angle is 0, and then it is the same as the theta is 90 degree, where theta is the angle between the two vectors. Okay, so you guys already learned that, right? But we will prove this guy, or we will prove these two of having 90-degree angle or perpendicular is the same as this the fact that the inner product is 0. Okay, let's prove that. So yeah, so I don't like this figure because yeah. So let's consider the origin here in the first vector and the second vector here. And then suppose these two vectors have the 90-degree angle, and then we can actually form the triangle, like so. It's like this kind of triangle, and the angle here is 90 degree in both sides, and then this one will become v and this one will become minus v, and here it's like a little bit of a trigonometric kind of relationship. If we have a 90 degree here, then the vector length between these two should be the same, right? And then this vector is u minus v, but here in this case we have a minus or negative v, and so the vector length is the length of this u minus v. Okay, and so in this in this triangle we will have this kind of relationship, right? So again, the starting point is that they have the 90-degree angle, and then we just negate one vector and then form the triangle, and these two edges should have the same length, and the lengths of each edges are represented by this. Okay, so from this this can be rewritten by this form. So again, the vector length is defined by this, right? The inner product of the same vector. Okay, and then u plus v and u plus v is computed as an inner product, and then they are distributed, and then something like that. Okay, u inner product u and u inner product v, or v v dot u and v dot v. Okay, so u dot u is again converted into this norm form. Okay, then this v dot v is converted into this form. And then we have u dot v and v dot u, and then they will be the same, and then we have this, right? And then we do the same thing on this vector u minus v, the distance between u minus v. Okay, and then the remaining part is the same, but we will only have the difference here. Okay, So this guy and this guy should be the same, and so we are canceling these out, and then the remaining part should be the same. So 2 times u dot v should be equal to minus 2 times u dot v, and so it will become, after moving it to the left hand side, 4 times u dot v should be 0, which means u dot v should be 0. Okay, so what did we do here? So we started from the fact that they have a 90-degree angle between the two vectors, and then in that case, by forming this triangle and then equating or making the edges of these two edges, the lengths of these two edges become the same, and that way we obtained this conclusion that their inner product should be the 0. So 90-degree angle, we basically proved that if the two vectors have a 90 degree, and then they should be the 0 inner product. Okay, they should have a 0 inner product. Okay, so if the two vectors have the 90-degree angle, or more mathematical term is that if they are orthogonal, then this inner product being 0 is the same thing. Okay, and then 0 vector, from this definition, if we use a 1 vector as a 0 vector, and then this 0 vector is orthogonal to every vector, because 0 vector with the vector v should always be 0. So you can consider the 0 vector to be orthogonal to any vector that you can consider. Okay, then this is basically a Pythagorean theorem. So you have u and v. Okay, in this case, u plus v, which means in this triangle, we consider the length of this vector, because in this case the length of this red is this guy. Okay, and then if we take the square of it, if the u and v are having a 90-degree angle, and then you guys know their inner product should be 0, and so this guy is just the same as this guy, right? Because this guy is 0 when they are they have a 90-degree angle. So this guy is the same as this guy if they are orthogonal, and so we obtain this, and this will become Pythagorean theorem that we learned in maybe middle school. Okay, so again, the squared lengths of these two vectors, u and v, then u plus v will have this vector. Okay, the squared length of this vector is the same as the sum of the squared lengths of these two vectors. Okay. The next thing, which is kind of main thing that we learned today, is called this orthogonal complements. Orthogonal complements. Okay, so let me ask one thing. So, okay, let me start in this manner. So now we consider the subspace. Okay, so orthogonality, or this kind of perpendicular thing, was defined between the two vectors. Okay, two vectors. But now we consider one of them. We change one of them as subspace. Okay, so we first have this kind of subspace that is maybe plane, and then we consider one vector, and then consider whether this vector and this subspace are orthogonal or not. Okay, so we consider this orthogonality between vector and subspace. Okay, now the meaning of this orthogonality between a vector and the subspace is as follows. So basically, in your subspace, you can pick up many different vectors. Maybe this guy and this guy and this guy and so on, right? And then suppose your vector is something like this, okay? And then this vector should be orthogonal to any vector that you can pick up from your subspace. In that case, we say that this vector is orthogonal to this subspace. Okay, so this is quite a strict condition, but you guys kind of understand it, right? So if we have this quite flat and horizontal surface as our two-dimensional subspace, what is the orthogonal vector? It's just like this, right? So if it is slanted in any directions, and then it will start to be visible by this vector, right? So this vector should hide itself from any vectors from your plane or your subspace. So that is the meaning of this orthogonality between a vector and the subspace. Okay, and then now we can also think about And then now this orthogonal complement is as follows. So the situation is you are initially given one particular subspace, and then you consider how many vectors that are orthogonal to this subspace. In this case, how many vectors do you think exist, which is orthogonal to this plane? So if we consider this horizontal flat surface, and then we can consider only one vector, right? If the directions changes in any ways, and then it will no longer be orthogonal, right? And then in this case, the number of vector that is orthogonal to this subspace is only one. Although you can think about some other vectors like stretching out the direction of the vector along the same direction, or maybe like the direction which is exactly reversed, right? In this case, they are also orthogonal to the subspace, but in terms of the direction, they are all the same, right? And also, you can think of some subspace as well. So now, we consider the vector and subspace and their orthogonality. And then, what if we have subspace as well in this part? And then now, we consider the orthogonality between the subspace and the subspace. Okay. In that case, how can you define the orthogonality between these two subspaces? So we become more strict. So you become one vector from one subspace, and then the other vector from the other subspace, and then they should be orthogonal. It should be true, or it should be orthogonal for any chosen vector from these two subspaces. Okay, so this is quite kind of strict, right? So what we are studying here is about this orthogonal complement. Orthogonal complement is as follows. So so we are not extending to the relationship between a subspace. We still consider vector versus subspace, and then given a particular subspace, you collect all the possible vectors, okay, and that is called orthogonal complement. Okay, so basically you collect all the possible vectors that are orthogonal to a given subspace. So that is orthogonal complement. And then complement means what? In the set, a complement is what? So given this set A, and then AC, or a complement is the rest of the element or rest of the subset from your universe, right? So the complement means if you add A and AC, in this case you will form the universe, right? And also A and AC doesn't have any redundancies or any common elements. Okay. In the vector space, so our first thing was some subspace S, something like a plane, and then this vector that is having this the unique direction, that is the only vector that is orthogonal to this vector, although they have many vectors along the same direction. But in terms of the basis, so we consider the basis. So this plane will have the two basis vectors, and then this is your orthogonal complement, and then among all the possible vectors along this line, if you consider the basis, you can pick up just one vector, and then that will span the entire possible vector set. Okay, so you pick up the basis from your initial subspace, like this plane, and then you pick up the basis from your orthogonal complement. And then if you add those two sets of bases, so you basically have two sets of bases, and then you add them up, and then you form that as the new basis. In that case, it will completely span the entire universe. So it's like this. So so let's consider maybe five-dimensional space. And then suppose your subspace was three-dimensional. Okay. So although we can not imagine directly, but among the five-dimensional subspace, you have a five-dimensional entire space. You have a three-dimensional subspace. And then what is the possible vectors that are orthogonal to this subspace? Which means you pick up any vectors from your three-dimensional subspace, and then that is that is meaning of this guy. Okay, so that way we consider this a complement. And then let's consider this thing. So there should be no redundancies between the complement kind of relationship. So in this case, it is just a kind of this kind of visible part. Okay, so every vector that are orthogonal to this subspace, that is not visible at all, right? So that way, if you pick up the basis from your subspace and the orthogonal complement, they should be always linearly independent. And actually, they are maximally linearly independent, because every vector, any vector that you choose from your orthogonal complement and the subspace, they will always have a 90 degree or orthogonal. Okay. Okay, so I'll stop here, and then we will finish the rest of the chapter in the next class. Okay, thank you very much.
Last class, you introduce 2.9, right? This one?
Yeah.
Only this one, 2.9.
Yes, right. Yeah.
Okay.
Right.
And you upload the video on YouTube? No?
So unfortunately, last time I had some problem with my computer, so it was not recorded, unfortunately. But the amount that I covered last time is almost overlapping with today's class. So hopefully you will see much difficulties in 2.8. Okay. So if you have questions later on, and then
Thank you very much.
처음부터 시험의 날짜가 5월 9일이라 하셨잖아요. 5월 9일은